In this video, we're going to be looking at power functions. What is a power function? Any function that can be written in the form k times x to the a is a power function. K is the constant or the constant of variation, and a is the power. Many common formulas from geometry and science are power functions. For the circumference, c equals 2 pi r. The power is 1 because we have a power of 1 right there, and the constant is 2 pi. 2 pi doesn't change. The area of a circle, the power is 2, and the constant will be pi. Force of gravity, power is -2. This can be written as k d to the -2, and the constant is k. And Boyle's law, you may have studied that in science. V equals k over p. The constant is k. Again, this could be written as k p to the -1, so the power is -1. Let's look at another formula. If we have the function f of x equals the fourth root of x, what's the power and the constant of variation? If it's written to the fourth root of x, we can rewrite it as f of x equals x to the 1/4. So the power is going to be 1/4, and the constant of variation, we have unseen 1 there, so the constant is 1. Let's go ahead and graph that. To enter the fourth root on this, there's two ways we could do it. We could either do it as x to the 1/4, and you have to make sure that the 1/4 is in parentheses, or you could do it as the fourth root. If we go down to y2, you put in the root first on the 83. On the 84, it's probably much simpler. On the 83, you put in the root first, and then we go to math, and 5. That's the nth root, and the nth root of x. And both of those, graph both those, will get the same thing. The next thing we're going to do is analyze this function. So I'll bring the calculator back up so we can take a look at that. Let's look at the domain. The domain, what are the possible x values? Our x values go from 0 to infinity. That's all the possible x values, and it can include 0. The range, all the possible y values, also include 0 and continues up till infinity. It is continuous on 0 to infinity. There are no gaps or holes in it. It is increasing from 0 to infinity and not decreasing at all. It is not symmetric. It is bounded below. It never goes below 0. Extrema, maximum and minimum. There is a minimum at x equals 0. There are no asymptotes, horizontal or vertical. And the end behavior, the way the end behavior works, we're going to write this, the limit as x approaches infinity, as x gets bigger and bigger, of the function, the fourth root of x, as x approaches infinity, the y will get closer and closer to infinity. I want you to try this one. I want you to state the power and the constant of variation for the function g of x equals 1 over x squared. Graph it and analyze it using the same information: domain, range, continuous. Find all of these for that particular function. Single term polynomial function is known as a monomial function. Any function that can be written either as f of x equals k or f of x equals k times x to the n is a monomial function. We're going to look at some graphs of power functions. For any power function in the form of k times x to the a, one of the following three three things can happen when x is less than 0. Either it's undefined, it's an even function, or it's an odd function. I'm going to bring up the calculator, and we're going to look at a couple of different functions. The first one I want to look at is x raised to the 0.5 or x raised to the 1/2. Less than 0. Oops. Need to turn the function on. Graphing it. This is in quadrant 1. If you look at my window here, x is from 0 to 10, y is from 0 to 10, is quadrant 1, and that's what x to the 1/2 looks like. If we look at the next one, x to the -2, turn that one on and that one off. X to the -2, it'll come in and it is, here's a good word for you, asymptotic to both graphs, to both axes. Both the x-axis and the y-axis are asymptotes. So it's asymptotic to both axes. And that was, what function was that? That was x to the -2. And the last one I want to look at is x to the 7/3. Graphing that, we have it going very steeply up. And the interesting thing happens if you look at all of these graphs where, and I'm going to include y is equal to x, and I'm graphed them all at once. The thing that you notice is that they all go through 1. Now, the x will be 1, the y will be whatever our constant is. If they have a positive power, it's also going to go through 0, 0, and if we have a negative power, it's asymptotic to both axes. If we have a picture of them, you can see a little clearer. The graph on the left is when our constant is a positive in quadrant 1, and the graph on the right, if our constant is a negative, we're in quadrant 4. Show you how to use this information. Let's take the graph of f of x equals 2x to the -3. So in this case, our k equals 2, and that's positive, so we're going to look at quadrant 1. Our power, which is our a, is -3. Because it is negative, it is going to be asymptotic to both graphs. It will pass through 1, 2, and will look like that. Asymptotic to both graphs, going through 1, 2. Then we need to figure out if it's even or odd. If we look at f of -x, we have 2 times -x to the -3. We have an odd function here, so that's going to be -2 x to the -3rd, which is the same thing as -f of x. So that means it's an odd function, and it will be symmetric about the origin. So we'll be going 1, 2 there, and there's our function, 2x to the -3. And let's check that on our calculator. We'll put in 2x to the -3. We need to change our window back to standard. And graphing it, and there it is. It's hard to tell on this that it is asymptotic. If we look at the table, you'll actually be able to see that it is not touching the 0. And now, just for fun, see you in class.